Hey everyone, welcome back to our series of presentations that we've entitled Subnetting Demystified. This is a series of presentations that cover all things related to IP addressing and binary math and subnetting. You can see the major points that we're going to be covering and that we have covered on the whiteboard. In this presentation, we're going to take up the topic of address classes, also sometimes referred to as classful addressing or classful networks. Now you may be thinking, address classes and classful addressing and all of those topics, that's not the way we do things anymore. Today we're all about CIDR notation and network prefixes and variable length subnet masks, and that's all very true, and those topics are going to be covered very thoroughly in our next presentation. But let me encourage you to go ahead and work through this presentation and don't skip over it, because even though it's entitled Address Classes, there's lots of foundational knowledge in here that will really help you as we proceed on to the next presentation, where things get a little bit more interesting and we start to get closer and closer to this topic of subnetting. And here on the whiteboard, I have entitled this IP Addressing the Early Days of the Internet Protocol. In previous presentations, we've already taken a look at some IP addresses, and when we did that, we saw something that looked kind of like this. I'm just going to write out a typical IP address the way we would write one out today, 192.168.10.1. And just as a matter of reflection, let us recall that there are two pieces of information encoded in this IP address. There's information about the network and information about the particular host computer that's connected to the network. And we've come to understand that this dotted decimal notation is just a convenient way for us to represent what is essentially a 32-bit binary value, but for human readability we represent it as a series of 4 decimal numbers ranging from 0 to 255, separated with the dots. Back in the early days of the Internet Protocol, and by early I'm referring to the time period of about the 1970s, in the time of the Department of Defense ARPANET project, which was the precursor to the modern internet that we know today. And an IP address from that era might have looked something like this. And back at that time, an IP address may not have been written at all, or it may not have been typed on a keyboard at all in the way that we think of it today. It's very possible that the device could have had a series of dip switches, and the switches are either flipped up or down to represent the values of each position of the IP address. And in those very early days, even though the IP address was a 32-bit binary value, a lot of those bit positions were unused. The first 8 positions, and only the first 8 positions, were known to represent the network, and the last 6 positions were known to represent the host. And these other 18 positions weren't used for anything at all. So if we have 6 bit positions for the host address, recall that powers of 2 table that we were looking at in a prior presentation, and we know that 2 to the 6th power is going to be equal to 64. Now, for some reasons that we'll talk about later, the situation where the host number is all zeros and another situation where the host is all ones, those are special cases. And those are not assignable addresses that you could configure on a host computer device. So we're going to subtract those 2 special cases from 64, and we would get 62 usable host addresses, which back in the 1970s, that was probably plenty, because most of the installations, they may have had only 1 or 2 or 3 relatively large computer systems, because this was before the proliferation of the local area network, where we had a computer on every desk and a printer at every corner on the hallway. Typically, we would only have a few very large systems, and this relatively small number of host addresses was seen as being plenty for that period in time. So now if we look at the network portion of the address, we have 8 bit positions for the network. So 2 to the 8th, you remember from the powers of 2 table, that would give us 256 possible networks. And having 8 bits for network addressing, giving us 256 networks, was seen as being plenty in those early days. But it wasn't very long before it became clear that this addressing model would not scale very well. With the proliferation of more host computers and the need for more networks, having just 6 bits for the host and 8 bits for the network quickly became insufficient. So the solution to this problem of scalability was pretty simple. We've got these extra positions that were not being used for anything prior. So what if we were to come up with a way to be able to use these additional positions to provide more network addresses as well as more host addresses? And that's exactly what happened. This led to the establishment of address classes, or classful addressing, that allowed for the boundary between the network and the host to be either placed here between the 4th octet and the 3rd octet, or here between the 3rd octet or the 2nd octet, or here between the 2nd octet and the 1st octet. So by organizing addressing in this way, networks could be appropriately configured with a number of networks and a number of hosts on each network that more closely met the needs of the organizations that were connecting their networks to what had now evolved into, or was beginning to evolve into, the internet that we know today. So this idea of classful addressing allows us to specify that the boundary between the network address, or the network portion of the address, and the host portion of the address could either occur right here between these two octets, here between these two, or here between those two. So how do we configure it so that we can decide where that boundary goes? And remember, this whole notion of classful addressing is that we can only put the boundary, that we can only put the dividing line on an even octet boundary. If we wanted to put the dividing line somewhere in the middle of this octet, using classful addressing, we can't do that. And we're going to talk about some techniques later on where we can do exactly that, but we're not there yet. We're talking about how can we put the boundary either here, here, or here. How do we do it? Well, here's how. The Internet Engineering Task Force is a group that develops a lot of the protocols and standards that make up the infrastructure on which the Internet depends, and the Internet Protocol is one of those standards. And in the early 1980s, 1981 I believe, the Internet Engineering Task Force set forth a rule, and these rules are set forth in documents called Requests for Comments, or RFCs. And this particular rule is RFC number 791 that established this idea of classful network addressing. And what the rule says is that if we construct an IP address where the first position in the most significant byte, that's this one right here, is equal to a 0, then it can only be a 0. And if that's true, this is going to establish something called a Class A address, and that will cause the boundary between the network portion of the address and the host portion of the address to be right there. So the most significant bit in the network portion of the address is 0. That's this very first position right here in the very first octet. That's going to be a 0. And then the rest of the positions can be any combination of 1s and 0s, and I'm just going to draw a number of ends here. So the first position is a 0, followed by 1, 2, 3, 4, 5, 6, 7 ends, and these ends could be any combination of 1s and 0s, and that's going to result in network numbers that range from 0 to 127. Well, how did I derive that? Well, think about the bit weights of these positions up here. This is the 128's position. This is the 64's position. This is the 32, 16, 8, 4, 2, and 1. So we've said that this 128's position is going to be forced to be 0. So if we set all the rest of these to 0, then that quantity is going to be 0. If we set all the rest of these to 1, then that's going to be 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. The sum of that is 127. So our Class A network numbers can range from 0 to 127. Now, as it turns out, network 127 is a special case, and you may recognize that as the loopback address, and the loopback address is interpreted to mean one's own address, and that's an address that's used for testing of the IP protocol stack on the computer being tested. So we can't assign 127 as a real network number. So basically our Class A IP address numbers are going to range from 0 to 126. So if you'd like to think about this in terms of powers of 2, this first bit here is reserved for Class A and it's going to be forced to 0. So we're going to have 7 remaining bits that we can use for network addressing. So that's going to be 2 to the 7th, or 128 possible values ranging from 0 to 127. And as we just said, 127 is reserved for loopback testing. So 0 through 126, that's our Class A network range. Now with respect to host addresses, this is a 32-bit binary number here. We've got 8 bits we've taken care of, so that leaves 24 for host addressing. So 2 to the 24th power is equal to 16,777,216 is 2 to the 24th power. But we've got a special case that we have to consider where the host number is all zeros or the host number is all ones, and neither of those special cases are a valid assignable host address. So we have to subtract 2 from that to get 16,777,214 actual assignable host addresses. So now let's consider the next network class, which is going to be Class B. And the rule states for Class B networks that the first position of this first octet is going to be set to 1, and the second position is going to be set to 0. So back in the Class A example, the rule states that the first position of the first octet must be a 0. Well, the rule for Class B says that the first position of the first octet must be a 1, and the second position of the first octet must be a 0. And when that's the case, the boundary between the network and the host portions of this address falls between the second and the third octet right here. So to work out the rest of this first octet, the 1 and the 0, that's fixed. If it's going to be a Class B address, then the first position has to be a 1, the second position has to be a 0, and then I've written ends out here for the rest of this octet to indicate that this could be the any number of 1s and 0s all the way out through the remainder of the first octet, extending all the way through the second octet, because with Class B address, we're going to use the first 2 octets, or 16 bits, for the network, and the last 2 octets, or 16 bits, for the host. So let's work out what the valid values for Class B network numbers would be. Well, since we have this bit forced to be a 1 because the rule says so, then the smallest number for a Class B network that we could come up with is what? Well, if this one is forced to be a 1, it's got to begin at 128 because we can't set this to 0. So if this is going to be a 1, and then all of the rest of the bits in the network number of the first 2 octets, if these are all zeros and that's a 1, then where is this going to begin? It's going to begin at 128. So 128.0, where all of these are zeros except for that 1, and then all of these are zeros, then that's our first network in the Class B range. So what's the last network going to be? Well, let's work that out. The first bit has to be a 1 because the rule says so. The second bit has to be a 0 because the rule says so. So if we were to set all the rest of these bits to 1, we would take 128 plus 32. We're skipping 64 because it's set to 0 here. So we take 128 and we add 32 to that. We add 16 to that. We add 8 to that. And then to that we add 4. And then add 2, and then add 1. What do we get if we add all those up? Well, we get 191 in the first octet. And then if we set all of these to 1s in the second octet, then we're going to go from 191, or we're going to go from 128.0 to 191.255. How did I get that once again? Well, let's just go through it. If we set all of these bits here to 0, this one has to remain a 1 because the rule says so. This one has to remain a 0 because the rule says so. We set all these to 0. We set all of these to 0. Then the first possible Class B network number is going to be 128.0 because we said these are all zeros, these are all zeros, and there's a 1 right there. So the largest possible number that we could get in a Class B network, once again, if this has got to be a 1, that's got to be a 0. So if we set all of the rest of the bits in the first octet to 1, and we just add up these bit weights up here at the top, 128 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, that equals 191. And then if we set all of these network bits in the second octet to 1, then that's going to be 255. So there's our range of network numbers for a Class B address. It's going to be 128.0 to 191.255. Those are just the network numbers. We've still got two other octets out here that would be used for host numbers, and we could have a maximum of 2 to the 16th, or 65,536 minus 2, which is 65,534 possible host addresses. How many networks could we have? Well, we can have 2 to the 14th networks. Why 2 to the 14th? Well, these first two bits, the value is dictated. So how many bits do we have to work with? We have these 8 bits in the second octet plus these 6 bits in the first octet. So that gives us a total of 14 bits of network addressing. So 2 to the 14th is 16,384. So in the Class B networks, we could have a maximum number of networks equal to 16,384, each with 65,534 hosts. So continuing on, let's examine the Class C network range. What does the rule say about Class C? Well, the rule says that for a Class C network, the first 3 bits of the first octet, the first 3 most significant bits of the first octet must be 1, 1, 0. Just looking back at Class A, the first position was 0, and in Class B, we just moved the 0 over to the second position and it became 1, 0. And for a Class C, we moved it over 1 more and it becomes 1, 1, 0. And for a Class C address, the dividing line between the network and the host is over here between the third and fourth octets. So we just move it down 1 every time. So the first 3 bits in the first octet are fixed according to what the rule says. They must be 110 for it to be a Class C address. So we've got 1, 2, 3, 4, 5 bits in the first octet that we could use for network addressing. We can use 8 bits in the second octet and 8 in the third. And only the last octet is used for host addresses. So what does the range of network numbers for Class C addresses look like? Well, if we take all of our network bit positions, that's from here, well, actually the first 3 are reserved, so that's from right here where this first N is, all the way through the first 3 octets. If we force all of those to be 0, what are we going to get? Well, if we add 128 and 64 together, we're going to get 192.0.0. So the first Class C network is going to be 192.0.0. The last octet, I'm not writing it out here because it's for host addressing. We're just talking about network addressing here. So if we set all of the remaining network bits to 1, what would it look like? So if we were to set all of the network bits to 1, and that represents these bits here that I've represented with the letter N, these first 3 are fixed because that's what the rule says. The rule says that the first 3 positions in the first octet must be 110. So if we leave those as they are and set everything else to 1s, we're going to take 128 plus 64. We're going to skip 32 because the rule says it has to be 0. And then if we have all these others set to 1, that's going to be 128 plus 64 plus 16 plus 8 plus 4 plus 2 plus 1. If we do the arithmetic and add all of that up, that's going to be 223 in the first octet. And then in the second octet, if we set all of those to 1s, that'll be 255.255 for the third octet. If we set all of those to 1s, And again, I'm just drawing the first 3 octets out here because all I'm calculating here are the network address ranges. The host is down here in the 4th octet. So the network numbers for Class C addresses are going to range on the low end from 192.0.0. Why 192? Well, the rule states that the first 3 positions have to be 110. So if we set everything else to 0, that's the lowest possible value that we could have. That's going to be 192.0.0. So if we take all of the values that we can change, which are these last 5 positions in the first octet, plus all of the second octet and all of the third octet, if we set all of those to 1s, then if we add up 128 plus 64, we're skipping 32 because it's got to be a 0 now. And then we add 16 plus 8 plus 4 plus 2 plus 1. Once again, that's 128 plus 64 plus 16 plus 8 plus 4 plus 2 plus 1. That's 223.255 if all these are set to 1, .255 if all of those are set to 1. So in the case of our Class C networks, we're using the first 3 octets for network addressing. We can see the dividing line way down here this time. We've got the first 3 octets for the network and the last octet for the host. So among those first 3 octets for the network, we could have 2 to the 21st possible networks. Why 2 to the 21st? Well, the first 3 octets make up 24 bits, but the first 3 of those 24 bits are reserved because the rule for Class C networks says that the first 3 bits have to be 110. So that leaves 5 bits in the first octet plus 8 bits in the second octet plus 8 bits in the third octet, the sum of which is 21 bits. So 2 to the 21st is equal to 2,097,152 networks for Class C. We have the last octet for host addressing, so that gives us 2 to the 8th, or 256 host addresses, but remember we have to subtract 2 from that because there are 2 special cases where all of the host bits are 0 and all of the host bits are 1, and we can't use either one of those as an assignable host address. So 256 minus 2 is equal to 254 possible host addresses for Class C networks. We've got 2 more address classes that we need to touch on briefly, Class D and Class E. And these are kind of special cases. They don't define the separation of hosts and networks like Class A, Class B, and Class C that we just went through did. Class D is intended for multicast addressing. Class A, Class B, and Class C are intended for something called unicast addressing, where we have one host communicating to another. With multicast addressing, we have one host communicating with a group of other interested hosts, and this is typically used for streaming video and for some other things. So for Class D, we just continue the same pattern. We just move the 0 over one more position, so the rule says that for a network to be a Class D network, the first 4 positions of the first octet have to be 110. So what does the range for that look like? Well, if we set the rest of the entire 32-bit number to zeros, except for these first 4 bits here, which are fixed, if we take 128 and 64 and 32 and add those up, we don't add 16 because it's a 0, so this position is the 128's position, the 64's position, and the 32's position. If we add all of that up, what do we get? We get the value of 224. So the first Class D address is 224.0.0.0. And the last one, well, what would that be? That's simply going to be where we take these last 3 octets and set them all to 1. And then, of course, we have to do our math over here. If we take 128, 64, 32, we're skipping 16 because it's forced to be a 0 by the rule. And then we take 128, 64, 32, and then 8 and 4 and 2 and 1. We add all that together, we get 239, right? So 239 for the first octet, and then we're going to set all these to 1, all these to 1, and all these to 1. So that would be 239.255.255 255. Remember, these are 255s because if we were to add the bit weight values up for all of these, if we took 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1 and added that up, that would be 255 if we set all of the bits in any of these octets to all 1. So the first Class D is going to be 224.0.0.0, and the last one will be 239.255.255.255. Class E works exactly the same way. Class E is easy to remember because Class E is experimental, and the rule says that for a address to be a Class E address, we take the first 4 positions and we set them to 1. So if we set the first 4 positions to 1, which is what the rule says, and then we take the remaining bits all the way out through the end and set those to 0, we're going to have 128 plus 64 plus 32 plus 16, that's 240.0.0.0. That's going to be the first Class E. And the last Class E will be, what would we get if we took all of the remaining bits from right here all the way on out and set those to 1? That's simply going to be 255. Remember 255 because, see, we've got the first 4 set to 1. If we set the last 4 to 1 as well, that basically says set everything to 1 in this first octet. Then we'll set everything to 1 in the second, everything to 1 in the third, and everything to the 1 in the fourth. So we'll wind up with the last Class E would be 255, 255, 255.255. And those are our 2 special cases, Class D and Class E. And just as a matter of wrap-up and review, if we look at Class A, Class B, and Class C, basically what happens here is, and we went through the arithmetic of calculating the number of networks and the number of hosts in each of these cases, and you can see that for the Class A, basically this would have been intended for the very largest organizations because we have a relatively small number of these available Class A networks. Works out well because typically there's going to be a relatively small number of very, very large organizations, but these very large organizations would need a very large number of hosts. So we've got a relatively small number of Class A networks, only 127 of them going from 0 to 126, each of which has a huge number of potential host addresses. Class B would be intended for the middle-sized organizations. We've got 14 bits of potential network address space. We have 14 because these first 2, remember, the rule says they've got to be 10. And then we've got 16 bits for the host. So we could have more Class B addresses, at least more than the Class A's, where we only had a handful of Class A addresses. We could have a maximum of 16,384 or 2 to the 14th Class B addresses, each with 2 to the 16th minus 2 or 65,534 assignable host addresses in each one. So this would be more for the medium-sized organizations. And then for the small organizations, we have 24 bits of network addressing, and we've got 8 bits for the host. And these would be intended for the smaller organizations because there are the smaller number of potential hosts. 2 to the 8th, or 256, minus our 2 special cases of all zeros and all ones, would be 254 assignable host addresses in a Class C network. So with this implementation of classful addressing, this increased the scalability of the IP address space quite a bit, because remember, in the very early days of IP, we only had 8 bits for the network and the last 6 bits for the host. So by implementing address classes, then we greatly expanded the number of assignable network and host addresses, and we created these various categories of networks: Class A for large, Class B for the medium size, and Class C for the small organizations. But it wasn't long until even this started to show problems, and it was not very efficient because it's not very granular in the way IP addresses were handed out. For example, maybe there were some organizations that needed more than 254 hosts in their network, but they didn't need 65,534. So those organizations might have gotten Class B allocations, but that was far more than they needed. So even though the Class A, Class B, and Class C addressing scheme helped to make the use of the IP address space somewhat more efficient, even this runs into some problems because we have only basically 3 sizes of network allocations, and that's not very flexible. And pretty soon it became apparent that we need is something that was more flexible than the relatively rigid structure of classful addressing, because with classful addressing we can only put the boundary between network and host in one of three places, either here, here, or here. So what we really need is something that would allow us to put the dividing line between host and network anywhere along this 32-bit line that we want. And that's exactly what we're going to take up in our next topic. Before we wrap up this presentation, there are two more things that I want to do. First, there's one more topic that I want to cover briefly. And then secondly, I want to put up some practice problems where you can go through and examine the idea of address classes. And I'll put some up on the whiteboard, and I'll let you know to hit the pause button, and you can work through those problems. And then we'll come back, and as we've done in previous presentations, we'll check our work together to make sure that we got to the same place. All of the discussions with regard to address classes and addressing that we've had in this presentation are assuming that we're talking about IP addresses that would be assigned with the intention that they could be connected to the global internet. Now, if you have a closed network that's not connected to anything, then you could assign any IP addresses that you wanted, really. But it's probably not a good idea to do it that way. What could happen would be that maybe we have a closed network that is not connected to the public internet, and we go in and just start assigning whatever IP addresses we decide to make up. But then it's always going to happen that even though maybe that network was not planned to be connected to the public internet, sometime in the future it may be. And then we would be faced with the problem of having to renumber everything because the numbers that we had used in the private network were not assigned to us by the Internet Numbering Authority, so that we would not be able to connect that network to the global internet with those IP addresses in place. So the solution that the Internet Engineering Task Force, the IETF, came up with was something called the Private IP Address Space, and it was defined in the RFC document, the RFC Request for Comments number 1918. And what RFC 1918 defines is 3 different blocks of IP addresses that are intended to be used in private networks. A private network could be a network that is not connected to the public internet, but more likely it's going to be a network or group of networks operated by a private organization that would use a gateway of some sort to be able to connect to the public internet. And here are the 3 blocks of addresses that are defined for use in private networks by RFC 1918. There is a Class A network, the entire 10.0.0.0 Class A network that begins at 10.0.0.0 and extends all the way to 10.255.255.255. That is the Class A private address space. There is a Class B private address space that begins at 172.16.0.0 and extends all the way to 172.16.31.255. And there's a Class C private IP address space that begins at 192.168.0.0 and extends all the way to 192.168.255.255. An organization is free to choose any of these private IP address space ranges and use them in their private networks in whatever way they see fit. And typically when that happens, there'll be a device that sits at the edge of that private network with a technology called network address translation that serves as a gateway from the private network to the public network. And the use of these private IP addresses combined with that mapping technology called network address translation that maps the private IP address space to the public IP address space is really responsible for the IPv4 address allocation lasting as long as it has. This video is created in early 2013, and it was several years ago when the IPv4 address allocations were depleted. The Internet Assigned Numbering Authority handed out the last of its available IPv4 addresses several years ago. Yet IPv4 continues to be alive and well because organizations can use many private IP addresses on their private networks and then access the Internet via a gateway with only one or just a very few public IP addresses. So it's this combination of the private IP address space combined with network address translation, or NAT, that has extended the life of IPv4 far longer than would have been thought possible some years ago. So for practice, I have put up on the whiteboard a dozen different IP addresses. And what I'd like for you to do is to go through each one, and in the column for address class, you'll write the appropriate address class, whatever it might be. Remember, we talked about several different address classes, 5 in total. Actually only 4, because one of them is experimental, and I don't have any IP addresses in the experimental range up here. So go ahead and just write down the letter for the address class beside each IP address. I'm just going to put an X there. And then determine, is this IP address from the global public IP address space? And if it is, put a check mark here. Or determine if it is part of the private IP address space, and if it is, put a check mark over here. So you're going to have only one check mark, obviously, either in this column or that column. It can't be both public and private at the same time. So go ahead and hit your pause button and work through these, and then we'll come back and take a look at our results and see what we have. Okay, let's check our work and see how we've done. I've written a little study aid over here to the right that will help me work through this problem very quickly. I've written out the 4 address classes, Class A, Class B, Class C, and Class D. And I've also written out the reserved bits that are required in order for a Class A address to be a Class A address, and the same for B, C, and D. So recall from earlier in the video that if it's going to be a Class A, the first bit position of the first octet has to be a 0. If it's going to be a Class B, the first 2 bit positions of the first octet have to be 10. If it's going to be a Class C, the first 3 bit positions of the first octet have to be 110. And if it's going to be a Class D, the first 4 bits of the first octet have to be 1110. So notice that we just start out with a 0 and we move the 0 over a bit position every time. So then we add up the bit weights. This is the 128's position. This is the 64's position. So if we have a 128 and no 120 and no 64's, the sum of that is 128. Here we have a 128 and a 64. And the sum of that is 192. And here we have a 128, a 64, and a 32. And the sum of that is 224. So what that's going to do is to let us look and immediately tell if the value of the first octet falls in the range of more than 0 but less than 128, it's going to be a Class A. Now remember, 127 is a special case. It's the loopback. So you'll never have a valid IP address other than a loopback IP address. Sometimes you'll be asked, what is the loopback IP address? So anything with 127.anything.anything.anything, that is a loopback address. So be aware of that and don't get caught by that one. So any IP address that has a value in the first octet of 128 or greater, but less than 192, it's going to be a Class B. And anything that has a value in the first octet of 192 or greater, but less than 224, it's going to be a Class C. Now I went ahead and added Class E to my chart here, not because we're going to be dealing with any Class E IP addresses, but it helps us work out the range. We can see that anything that is 224 or higher is going to be a Class D as long as it's 224 or greater, but less than 240. So by using this chart here, we can determine pretty easily whether any given IP address is going to be in the Class A network or a Class B network, a Class C network, or a Class D network. Then the next determination that we'll need to make is, for each of these IP addresses, is it public or private? And I've written out the 3 private IP address ranges. Remember, we've got the 10 network, the entire 10.0.0.0 network, all the way to the end of that, which is 10.255.255.255. That's all one big private Class A network. We've got the Class B private IP address range, which begins with 172.16.0.0 and runs all the way through 172.16.31.255. So be careful with that one. That one could be a little tricky because it could begin with 172.16 and it could be either a public or private, because the determination of whether it's public or private occurs out here in the third octet. So if this third octet, if it's a 172.16.0 but 172.16.31.255 or less, then that's going to be a Class B private. And the Class C private networks are all 192.168.something.something. So let's look at this first one. 128.88.16.2. We look at our chart and it is 128, but it's less than 192, so this is going to be a Class B, and it's a Class B public because as a Class B, it does not fall within the range of private Class B addresses that we have here. How about the next one, 207.17.100.1? Well, if we look at that first octet, it's 207. If we consult our table over here, we can see that that is greater than 192, but is less than 224. So this is going to be a Class C, and it does not fall within the private Class C address range. So we'll put a check mark under public for that one. So what about the next one, 172.16.32.88? Well, we can see that this first octet is greater than 128, it's less than 192, so it must be a Class B. And now the question is it public or private? Well, we have to be careful here, because if it's 172.16, it could be either one. This particular one is going to be a Class B public, because it falls outside of this range of 172.16.0.0 and 172.16.31.255. It's in the next network. It's in the 172.16.32. So it's going to be not a Class B private, but a Class B public. What about this one, 12.90.77.101? Go to our table. We can see that it is more than 0, but less than 128, so it's going to be a Class A. Is it public or private? Well, that's easy, because if it's a Class A private, it's going to begin with a 10, and this one does not, so it is also going to be public. How about 223.116.100.114? A quick look at our table tells us that it is more than 192, but less than 224, so it's going to be a Class C. And it's not a private Class C, because all of the private Class Cs begin with 192.168, and this one doesn't, so it's going to be public. 10.101.202.203, Class A, B, or C. Well, we look over here, we can see that it's more than 0, less than 128, so this is going to be a Class A. And we're going to look down here and see that, okay, this is our first private, because it is a Class A, and it is in the first octet is 10. So this is going to be a Class A private IP address. How about the next one, 192.168.114 and 77? It falls in the range for a Class C because it's greater than 192. It's less than 224. And if we look down here, we can see that it is a Class C private, because any networks that begin with 192.168.anything.anything, those are going to be Class C private IP addresses. 188. Greater than 128, less than 192, so this is going to be a Class B, and it does not fall within the Class B private range, so this is going to be a public. 160, 16, 88, and 33, once again, it is more than 128, less than 192, so it's going to be a Class B, and it's going to be a Class B public, because it also does not fall within the Class B private IP address range. 172.16.31 and 250, we can see that it's more than 128, less than 192, and it does fall in the range of 172.16.0.0, 172.16.31.255, so this is going to be Class B public, Class B private, because it does fall into that range that we just described. What about this one, 172.16.34 and 1? Again, it's more than 128, less than 192, so it is a Class B. And does it fall within our private Class B address space? You have to be careful with these Class B publics and privates, particularly when they're the 172.16 and they're close to the cutoff point. I tripped over that last one, so let's be careful with this one, 172.16.34.1. Does it fall between 172.16.0.0 and 172.16.31.255? Well, it is outside that range, so it's going to be a Class B public. What about this last one, 227.77.27.22? We can see that this is greater than 224, but less than 240, so it's going to be a Class D. This is our first and only multicast IP address that appears in this list. And we don't make the distinction between public and private. There is no private Class D space, so there's really nothing to do down here for that one. And now that we've checked our work, that takes us to the end of this presentation. We've had a look at the whole idea of classful networking. We've talked about how do we determine what is a Class A, Class B, Class C, Class D, or Class E. We went through a fairly rigorous discussion of some of those examples earlier in the video, and we can see that once we understand what's going on, we can reduce that to a little shortcut table that we can refer to determine what's what. And also let me draw your attention to the fact that in this entire discussion of classful networking, we have not mentioned a subnet mask even once. Many of you that have configured IP addresses before, you'll know that you always configure an IP address and a subnet mask. But remember, we're doing classful networking here. And by definition, if it's classful networking, there are no subnetworks. In the early days of IP, there were no subnet masks, and just by virtue of the fact that a device is configured with a certain IP address, then it could examine these first few bits and determine whether it's a class A, B, C, D, or E, and then it knew where the host portion began and the network portion of any IP address in. So this whole idea of subnet masks leads us into our next topic, which is going to be CIDR notation or classless interdomain routing. Also, we'll touch on something called variable length subnet masks, and we'll get a little bit more into exactly what is a subnet mask and when do we use them. Well, that wraps it up for this presentation. Thanks for tuning in, and be sure and check out our next presentation where we're going to move beyond this idea of classful networking, and we're going to learn how to be classless. And we'll talk about what that means in our next video. Thanks again.